Hello, this is Sereneth, and we are playing Creativerse Gone Wired. This video is part of a series of step-by-step tutorials that assume no previous experience with circuitry, virtual or otherwise. This video is part 2 of our video series on the number comparison gate, what I call the comparator. This time, not only will we be answering a question from our last video, we will be looking at the Numberpad and how it works with the number comparison gate, and even making a few simple machines like the locked door and a crude elevator. Here was our problem as we left off in part 1. We have 2 switches, spaces for 4 gates, and 4 LEDs, which we would like to come on very specifically when each switch is a certain way. The red should only light up when both switches are off. The yellow should light up when the second switch is on, but when the first switch is still off. The green should light up when the switches are the opposite way, with the first one on and the second one off. And finally, the last one should light up only when both switches are on. So if we go back and look at our truth table, we're looking for the results where we only get one true output and all the rest are false, and we want them for a very specific case. For 0, 0, we want only 1. The only table that works that way is the NOR. For 0, 1, we want the 1 where everything else is 0. That is our less than table. And the next one down, 1, 0, output 1 where everything else is false. That is greater than. And finally, for our last LED, we want it to light when the inputs are 1, 1, and at no other time, which is our AND gate from the logic gate. Now that we know which gates we want to use, let's go ahead and connect them. For 0, 0, we know we want the NOR gate. We'll put this switch to input 1 and this switch to input 2. For our second one, we want less than. Less than. Again. Make sure you have your inputs correct. This one will be greater than. Save. And finally, a logic gate of AND. AND is our default, so we don't have to go in and change it. Let's turn them off and test. Looks like it works. For 0, 0, NOR gate lights our red light. For 0, 1, our less than lights our yellow light. For 1, 0, greater than lights our green light. And finally, for 1, 1, with both on, our AND gate lights our blue light. We'll come back to this later. One thing I haven't yet talked about is the Numberpad. Its dialog window has 2 variables, a sends output and an auto reset time. The auto reset time also has a slider going up to 6 seconds. Let's give ourselves a comparator for this LED. Oops. And let's hook up our Numberpad to it and give ourselves a switch. It's already lit up. The default state for the comparator is equals. Since our switch is off, outputting false, it is the equivalent of a 0. So 0 equals what to be true? The default state for the number pad must be 0. Strange though, looking at it with our information pane from our wiring tool, it doesn't have a state. It doesn't appear to be outputting false or true. That's because the number pad's information, what it sends out in its signal, is a value. Turning our switch on, the signal is the equivalent of a 1. We haven't changed our number pad, so it's still outputting 0. Why don't we try changing the comparator to not equals? It outputs true. 1 does not equal 0. Let's change this to 1 to match our switch. 1 does not equal 1, that's false. Let's change this back to equals. 1 equals 1, that's true. How about 2? Because we have the number pad, we can do many more numbers than 1 and 0. What happens when we input 2? 1 equals 2, false. Switches in pressure plates and other parts of mechanical systems can only work with 1s and 0s, but the number pad allows us to work with other numbers. But this won't quite be enough. Let's try 2 number pads. We'll input 2 here. 2 equals 2. Perfect. Let's try less than. 2 is less than 2? No, a number can't be less than itself. So let's do 2 is less than 1. Oh, no, that's backwards. 2 is less than 3. Ah, now we have true. And of course, we can change it again to greater than. Now it's flipped. So let's flip it. 3 greater than 3, false. 3 greater than 1, true. So far, we've been working with the number comparison gate as an event handler. An event is basically a signal, a change in signal, or a new signal. We would like to change this to value, and instead of using a second external input, we'll make it whatever we like. Let's make it 5. Bring this back to equals for now. 3 equals 5. There's our 5 in input 2. False. 5 equals 5, outputs true. We have less than and greater than. We can do a lot more than just matching numbers. Let's have a little fun. I like my color over here. I think I'll change it while I'm at it. How about quick color tip? When you have a set of color, try mixing up the numbers and mix a good match. This one is 45, 138, 72. We'll make this one 138, 45, 72. We need to hook up our number pad and our comparison gate to the LED. And let's make this one 10. Well, of course it's still outputting false. Let's try again. Nope. Let's try 10. 10 equals 5, false. 10 equals 10, true. Let's play with our less than and greater than. Less than and less than. 10 is less than 5. That's false. 10 is less than 10. No, a number can't be less than itself. That's what equal signs are for. Let's do 3. 3 is less than 5. True. 3 is less than 10. True. How about a number in between? 7. 7 is less than 5. False. 7 is less than 10. Very true. This is a great way to get different outputs from one number input by using greater than and less than operations. Let's see. I haven't looked at that auto reset time. It does seem very familiar, doesn't it? It seems very much like the reset delay of our pressure plate. Here this one's 1.5. Step off and 1.5 seconds later it turns off. What about this one? We'd entered 7 last time. Huh? Shouldn't they both be off? What happened? That's right. When we first played with our number pad over here, we learned that the default number was 0. A 0 value, and 0 is less than 5, and 0 is less than 10. Haven't really played with greater than, so let's go ahead and change those now. And choose a higher number, 15. 15 is greater than 5 and greater than 10, so they should both light. Yes, and 1.5 seconds later, they both turn off. What happens if I add some zeros to the front of it? The number pad is not a code like many other codes and passwords. What you're seeing is strictly numbers, not just characters. The value of 0000015 is mathematically equal to 15. Here's a door that's already been connected. Let's see, we have a riddle. Why was 6 afraid of 7? Say it out loud. Very good. Oh, and it looks like it has an auto reset delay. The number pad connects to the number comparator. The number comparator is set to equals and is given a value of 789, and then connects to the door. The auto reset time is set for 2.5, and inputting the correct code, which is the value input of the comparator's input 2, it opens for the set time and then closes again. We know that number pads, when they're first placed, or when they default back after a reset, are 0. So let's change our value to 0 and see what happens. Our door opens. The number pad, as reset, is outputting 0, equals 0, outputs true. What if we put a different number in? It closes for the reset time, because during that time, any other number does not equal 2. Any other number equals 2? Output false, and close the door for that time until the pad resets. The numbers equal because they're both 0, and it outputs true to the door, opening it. With equals and a value of 0, this is a good way to invert your output if you want something a little different than what we had before. Here I've set up a basic elevator. It's only 3 floors, including the bottom. I have a single shaft with fans that will propel me up, and a fan that pushes me out for each level. Setting up the fans to push me across each level is easy enough. After connecting the fan, I just take the comparator, set it equals to the floor number, and change it to a value. But what about the fans in the shaft? Can't I just leave them on and head up? Ah! The velocity has pushed me past the level fan, the horizontal fan, and I can move, but this is not ideal. We can do something better. In this smaller simple model, we only have 2 fans in our shaftway. We definitely want this fan on when we first go up. We probably only want this fan on if we're going to go all the way to 3. How shall we set this up? So when looking at the fans in our shaft, when should each fan be on? We need to decide our desired floor. And here I'm using the naming convention common in a lot of North America and in Japan and Russia, where our bottom floor is the first floor, above that is the second, and finally the top is our 3rd floor. We have 2 fans to work with, one at our base, and one about halfway up, just under floor 2. Now if our desired floor is floor 1, whether we are there or coming down from a higher level, we definitely want that fan to be off, so it should be receiving a false signal. Same thing for the fan halfway up. It should also be turned off at this time. But if we're going up to level 2, then we definitely want the fan at the base to be on, so that should receive a true signal. Now we already know from working with it that if the fan halfway up is also true when we're trying to go to the 2nd floor, it will push us too hard and we'll get stuck on the ceiling. So this one should definitely be receiving a false signal. Finally, for the 3rd floor, we need the momentum of both fans. So the base will be receiving a true signal and the fan halfway up should also be receiving a true signal. What do each of these fans look like as a number line? Here's our fan at the base, where 1 should be off, 2 and 3 should be on. And how do we say this with a comparator? Well, we can say greater than 1. 1 is not greater than itself, so it will definitely output a false signal, but 2 and 3, which are both greater than 1, will output true. We could also say equal to or greater than 2, greater than or equals to 2, which is mathematically, working with whole numbers like this, the same thing. What about our fan halfway up? What about its number line? It turns on a little bit later than our fan at the base, so it looks like it's shifted over a bit. When it's 1 or 2, it should be off. But when the number we punch in is 3, we definitely want it on. It's shifted over, so let's shift our numbers over for the comparator. Greater than 2, or greater than or equal to 3. Now wait a minute, you might say, wouldn't it just be easier, for example, the fan at the base, to have it say not equal 1? Then it would be on for 2 or 3 or 4 or what have you. There's 2 reasons for this. I may want to expand down and create a basement, and it may be easier just to designate the basement as level 0. If I drop down to level 0, 0 is not 1, so my fan would be on, actually preventing me from going down. The second reason is for the number pad itself. Remember that the number pad, when it resets, goes to a 0. Now we haven't used the auto reset delay in this design, but in future developments we may want to incorporate it, so we will leave that open for now. Use greater than or equal to. What about the fan halfway up? Wouldn't it just be easier to, say, designate the comparator equal to 3? Well, what if I want to add on? Let's connect our shaft fans. We want this bottom one to come on anytime we have a number greater than 1. So it will come on when we select 2, 3, 4, or however far we want to expand. We want this fan to come on, if I can find its button. Ah, I selected the wrong nodule. We want this one to come on only when it's greater than 2. Don't forget to set it as a value. When we're going to 3, it comes on to bring us up. When we're going to 2, it stays off, so our velocity slows. Excellent. Now let's go to 3. Good. And we're ready to expand further up if we need. We have, as far as I can tell, fully explored the number comparison gate and its often paired number pad. Take the time to test each combination of inputs for each operation yourself, and write down the truth tables by hand, much in the same way that we have in the last few videos. It may seem tedious, but a careful hands-on approach will make you more familiar and comfortable with the logic and number comparison gates. Don't forget to make use of inequalities, like greater and lesser than, when working with a set of outputs that need to be flexible, like the fans of our elevator shaft. In future videos, we'll finally approach the flip-flop and learn how computers count. Until then, take care.